all of you need to have been very familiar with what was on that previous slide. Some of you will have had the contents of this upcoming slide from your teachers. Some of you will have seen it in books. Some of you will not have seen any of this before. We already pointed out in the last slide that lone pair are more repulsive than bonding groups. The reason being, the lone pair, 2 electrons focused, centered on that atom. Bonding groups are spread out between the central atom and the terminal atoms, and so less electron density in the bonds. Same idea, that more electron density will be more repulsive is evident when you have double versus single bonds. Double bond, 4 electrons spread out between atoms. Single bond, just 2 electrons spread out between atoms. So for example, formaldehyde here, the carbon has got single bonds to hydrogen, double bond to oxygen, 1, 2, 3 groups of electrons, so the ideal or expected angle would be 120. However, lone pair, the double bond more repulsive, pushing those away, so the angle due to the double bond pushing away, 122 degrees, bigger than 120, squishing these single bonds together at their angle of about 116. Ethene or ethylene, that of course a lot of you have seen many times, I hope. Carbons again, they should be trigonal planar, so angles of 120. You've got double bond here that pushes those away, and so the angles associated with the double bond, 121.5. The angles not associated with the double bond, where these single bonds have been pushed together more, only about 117. Interestingly, I'm going to put this up. You have this tetrahedral phosphorus. This is drawn as if, going back to the Lewis structure debate, it was from the people who love formal charges. Indeed, this is one of the arguments that they use in favor of that phosphorus-oxygen bond being a double bond, right? And that is that it pushes the chlorines away. So 114 degrees there for the oxygen chloride, and only 104 for the chlorine phosphorus chlorine bonds. Now, to mitigate this a little bit, first of all, the electrons are spread out more in the phosphorus chlorine bond because it's longer than the phosphorus oxygen bond. That's something to think about, and so therefore they are going to be less repulsive because there's less electron density, because it's spread out more. So that matches up to what you're seeing. And then, as we said when we talked about the debate reality, it's going to be kind of like resonance. There's going to be somewhere in between the phosphorus oxygen single bond that you draw if you obey the octet rule, and the phosphorus oxygen double bond that the formal charge crazies would like you to believe. But anyway, you can again see the main point here: double bonds more repulsive than single bonds. Lone pairs generally more repulsive than double bonds, although very few examples in which that truly is the case. It can be truly exemplified, so I'm not going to dwell on that here. Another significant effect, electronegativity. Bonds to the more electronegative atoms are going to suck away electron density from that central atom. Thus, there is less repulsion there. So, for example, if we look at CX2O, we've already looked at formaldehyde. Now let's look at the difluoro version. Okay, so the idea here is that there's not going to be very much electron density at the carbon because these fluorines are just sucking it away. And sure enough, when you look at the angles, 122 and 116 here is discussed with formaldehyde, but now make those single bonds even less repulsive so they can get closer to each other because the fluorines are just sucking the electrons away. Okay, same if we look at an NX3 series comparing chlorine and bromine, chlorine and fluorine, excuse me, right? Chlorine is close to electronegativity with nitrogen, so you're going to see almost an ideal type situation here, about 107 degrees. Go to the more electronegative fluorine, so these bonds are polar bonds, more electronegative, more electron density up at the fluorine end, so therefore less electron density around at the nitrogen end of these bonds, which means that a lone pair can push them even further away from each other. And another little example associated with phosphorus. Notice here there's two effects going on here. First effect is phosphorus is less electronegative than nitrogen, which means that a phosphorus chlorine bond is more polar than a nitrogen chlorine bond. So you can see the diminution of the angles here. Okay, same thing over here. Even though we already had a very polar nitrogen fluorine bond, a much more polar phosphorus fluorine bond means that at the phosphorus, these bonds are going to be even less repulsive, so they get pushed closer and closer to each other. Another effect here is simply the size effect that I mentioned up here. Phosphorus chlorine bonds, nice long bonds, so electron density spread out quite a bit over it, thus they are not as repulsive as one otherwise would expect.